Thanks, Raju. Thanks, the organizers, for the invitation. I start with this remark that we generally start doing algebra by assuming names for the unknowns as X, Y, Z. And I take the same notion here and I use it for something that I'm going to discuss. So let's start with this para that you got to see in yesterday's talk by Bedango, where he highlighted these sentences which says lattice QCD methods provide a unique tool to study hadron masses from first principle with controlled systematics, and lattice QCD methods can already calculate nucleon mass accuracy at percent level. And he stopped at that point. And this is very much true, and I give some examples where you can see there are several lattice calculations which actually have been successful in evaluating all these hadron masses. And it's not just hadron masses, lattice QCD can even evaluate hadron isospin splittings, for example, neutron proton isospin splitting, which clearly give an impression of where lattice QCD calculations stand in terms of the hadron mass determination. Now I invite you to read the next sentence where he stopped. It says, however, it is still interviewing how collective interactions of tiny quarks and gluons emerge into a massive hadron. And my talk is basically about this part. All right, now this won't change. Yeah, now it works, yes. Okay, thanks. So, so nucleons are not alone. We have been discussing about nucleons and pions primarily, and nucleons are not alone. And here is a list of the family of particles that where nucleons fall into. And you don't have to read all of these things. Primarily what I'm focusing on, there are certain particles which are named X, Y, and Z, and there are something new called PCs here if you can really read it. And these are the things that I'm going to discuss. All right, so many of these XYZs that happen, or all of the XYZs that I named to, fall into this category of charmonium-like particles. This is actually a spectrum that I actually took from Olson's, Stephen Olson's review, which is already like seven years past, but still actually the relevance has not yet gone. And there are several states that are colored in black, which are sort of more or less well understood, while there are other colored states which are named as either X, Zs, or Ys. These are the states which have some kind of confusion in the sense that if you try to explain some property of this particle in terms of something, we actually fail to understand some other property based on the same arguments. So I give one such example. This is actually the longest non-exotic in this category, which is named as X3872. And it was found to be, it was discovered in 2003, so 20 years back, and quantum numbers were only finalized only in 2013. It was found right below the lowest 2-particle threshold. And the most interesting thing that one can immediately point to is the fact that this can actually decay into two different, not two, actually I'm just highlighting two of it, which is most important. And you can see it can decay into a Jepsi omega kind of system, where Jepsi is a charm anti-charm kind of particle, and omega is an isospin light vector meson, while Jepsi rho, where rho is actually an isoscalar is omega, and rho is an isovector. Now the thing is actually, since it can decay into two different channels with two different isospins, then its isospin is under question. So we don't really know what its isospin is. So this is already a clear indication that there is something going, something that we don't understand about this. Hence the name X for this particle. There are several other examples in this category. One of the most recent one is the TCC, which I will actually discuss a little bit more later on, because there are some interesting calculations on lattice on this regard. There are also particles called X6900, which was found to be which was observed in this di-Jepsi production cases. There are also certain candidates, or not candidates actually, these more or less established pentaquarks in the lambda, Jepsi proton final state. Similarly, X2900 in the singly charm cases. Well, there are also some other candidates like X3915 and X3960, which was found in two different scattering channels, but they basically fall into near to same energy category and also have some similar properties, which means that it might be the same candidate, except that they were found in different experiments, and due to certain technical difficulties, it may have been interpreted as different particles. Okay, so by now actually we have very many particles like this. These are actually a collection of all the conventionally understood particles, as well as many other X, Y, Z and particles as in the chronological time of its discovery. And you can see there are so many particles with T, the name T, etc. and etc. I believe, okay. And if you want to actually get more details about this thing, this is just an experimental part. I just want to motivate you about XYZs, because this is not part of, this is not the main motivation of this whole workshop. So if you want to know more about it, you can actually listen to the talk by Liming Sang recently, and also look into this web page where this has already, this plot is taken from this website and is discussed well there. So our main question here is this. So this is actually a screenshot of Frank Low's articles on these exotic hadrons, and these are called exotic hadrons because they basically don't tend not to actually obey the rules. And this is exactly why they are called exotic hadrons. And the question we are after is, do we really need to call them exotic, or can we really understand them based on first principle QCD? This is the question that we are after. And now let me give you the reason, means the name details. So XYZ are particles, charmonium-like particles, which are found to be like exotic in nature. And T stands for tetraquark kind of candidates, and P stands for pentaquark kind of candidates. Although you might be already clear with this thing by now, but I just want to mention this. So my talk will be mainly on mass determination and couplings to the strong decays. Okay, one thing that I missed to say is that in all these particles that are observed, actually most of the particles that are observed are close to some kind of strong decay threshold, and for that reason, it could be the fact that these particles have some, or at least these observations have some connection to the strong decay channels. Either way, it could be a real particle or it could be some threshold effects or anything, whatever it be. But if we could understand these particles or these observations in terms of first principle QCD, then we can at least try to get away or remove this name exotic from these particles. All right. So yeah, so my talk will be mainly on mass determination and the coupling of these particles to various strong decay channels. And I assume throughout the talk, I assume isospin symmetry because all the lattice calculations, most of the lattice calculations are very much exploratory in nature, doesn't really deal with precision measurements. And I assume that isospin symmetry is there, which means that a mass of Q quark and mass of D quark are the same. So from the EIC perspective, there are already experiments. I have been motivated, means I have been working on this for past like near to 10 years, and mostly been motivated by observations and discoveries from LSCB, Belay 2 and BESS 3 and EIC. EIC also have prospects, so there are already some proposals from theory groups like photo production of charmonium like states from EIC, semi-inclusive electroproductions. There are already some proposals from these collaborations or people. Also, there are also arguments that if we could really scan, okay, we already know that heavy quarks can be used as important probes to scan the nuclear medium. So if we actually flip the argument, if you really could actually use the medium to understand this kind of hadrons, if the hadrons pass through the nuclear medium, if you could actually say something about the particle itself, that would be a great way to understand the nature and structure of these so-called particles as exotics. Okay, so there is already some prospects from the EIC side. And in fact, actually, we are also making some progress with regard to understanding the nature of exotics recently from Lattice QCD using studying their quark mass dependence. Okay, so from now on, I am actually switching to the Lattice QCD part, and there will be some slides I will definitely have to skip, I guess, because is this a time left or is this a time left? Okay, fine. All right, so I believe I have time. So you already heard this part from Nilmani, that we basically try to compute 2-point correlation functions or certain observables. So the main observable that is of interest for spectroscopy is 2-point correlation function, where we insert certain probes at a source point at another sink point. And basically the last time behavior of this kind of correlation functions basically gives you the energy of the hadron that you are looking at. Now, if you are looking at some asymptotic state or some stable states, you can really look at very last times and try to extract the mass or the energy of that particle by looking at this last time and just doing some symbol nonlinear fits. This way you can actually extract the ground state. Just to give you a feel that Lattice QCD has been quite successful also in the heavy hadron side. Here I give you an example of prediction. So the plot that I actually showed you in one of the first or the second slide was basically all our predictions. Here I am actually talking about a prediction where this is actually a discovery peak of a particle called doubly charm baryon, and all these lattice calculations predate this discovery, which means that all the lattice calculations were predictions, and you can see how well they agree. Of course, there are large uncertainties in the lattice calculation because different lattice calculations use limited amount of resources possibly, and also some of them also include a lot of consider systematic errors which add to the uncertainties. Okay, so that's why different lattice calculations have different kind of uncertainties, but yet you can see sort of they agree with the observed position of this doubly charm baryon. All right, if you are interested in knowing about more of this thing, you can go into this link. All right, now we are not just interested in ground state or asymptotic baryons, because most of the things that, or the exotic particles that we have actually seen, they like very close to strong decay threshold, which means that we have to actually consider some strong decay, their coupling to the strong decay, or we have to consider multi-hadron couplings to these kind of features. The challenges are when you actually want to scan higher and higher energy ranges, the challenges is that there are lots of states in the higher energy range. So we have to really scan a densely populated region of energy. And there could be radial excitations, there could be orbital excitation. We will have to also deal with higher spins. This is actually a quite difficult problem. On top of this, on lattice, we don't have the full O3 symmetry. We have some reduced symmetry. So spin identification also becomes quite complicated. Let me not go into the details of this part. The most important part is multiple scattering channel, which is actually the main focus of my talk. All right, so main thing is actually we want to extract scattering parameters from some finite volume simulations. And of course, there exists some formalism and its generalization, and this is what I will be basically focusing on in the rest of my talk. And there has been encouraging achievements both in the light and heavy hadron spectra in the conventional regime. Whatever I will be focusing on is on the exotic sector. All right, for excited state extraction, I already said that if you just look at the 2-point correlation function, you can just simply extract the ground state from its last time behavior. But if you want to extract excited states, of course, you can go on adding some more and more exponentials. So ground state you can simply extract by assuming a single exponential behavior at the last times. But if you want excited states, then you can actually go on adding more and more exponentials and try to fit even including some early time points in this figure. All right, okay, whatever I have plotted is basically something called an effective mass. So this is the correlation function, and an effective mass is basically log of C of t, basically a ratio of alternating time slices on the lattice. I'm actually skipping all the lattice details because Nilmani has already covered all these things in a very, very well way. All right, so, but for the excited states, if you are including more and more exponential, then your stability of fit goes very much bad because you have more and more parameters to fit. So what instead you can do is, instead of computing a single correlation function, you can actually try to use, try to construct a matrix of correlation function, where what you do is, instead of just using one operator, you use as many operators as possible, which has the right quantum numbers. We know that we can construct multiple different operators which has the same kind of quantum numbers. So if they have the same quantum numbers, they can couple to any state. In fact, actually, if there is a state that we are interested in, we can use multiple different kind of operators. The only thing is, there is this coupling that is associated with this correlation function, and depending on the operator that you choose, your signal will be better or bad. All right, so this way what you can do is you can use multiple different operators and try to extract a correlation matrix, and we can construct the correlation matrix in such a way that it is Hermitian, so the eigensystem is automatically orthogonal, and basically the physical state in this Hermitian correlation matrix are represented by basically the eigenvalues of this system. All right, so you can simply diagonalize this correlation matrix and extract the excited state information the same way what you did for the ground state. So this has already been accomplished, and I just give an example of omega CCC spectrum. This is actually a calculation that I did during my PhD with Nilmani. And here, in fact, actually, it's not just that we can extract the excited state, but we can also argue what is the nature of these particles. If we have good signals, we can really argue what is the nature of the various excited state that we extract. You can actually see this link if you are interested in knowing about more of these things. Now, so till now I have been talking about the excited state. So we have accomplished quite a lot of things in terms of extracting the excited state, but something that is crucially missing is the fact that we don't incorporate any 2-hadron. I did not really talk about 2-hadron interpolators because all this time I have been just talking about including more and more operators. And this example I gave you is just using something called single hadron operators, where I use, for example, this is actually a baryon where we use just 3 quark kind of operators. You can, in principle, consider a 3 quark and a meson kind of operator, which is like a baryon meson kind of operator, if you want actually a better reliability on your results. So this is the next crucial step, where you include 2 hadron interpolators and determine the effects of this. All right, so this is very clear. So we have many exotic candidates which lie very close to the threshold. This is actually the TCC doubly charmed tetraquark that was discovered in 2021. And the vertical dashed lines are basically the nearby lying two strong decay two particle thresholds. So it's clear that the peak is right close to the threshold. So it's very important that we include these things. These two different thresholds correspond to two different charges. But if you consider isoscalars, which is actually found, so this peak was found to be consistent with an isoscalar quantum number, and also favors Jp equal to 1 plus quantum number. So we know what is a quantum channel that we are interested in, and basically we try to actually pin down what is going on in this case. In fact, it's not just interesting from the experimental side. There has already been calculation on similar systems from the lattice as well as non-lattice perspective. I'm just giving some motivation from the lattice side. So there has already been calculations on similar TBB where the charm quark is replaced by bottom quark. Here, this is actually our number where we found, means all of the entire community finds that there should be a deeply bound state in this kind of system. While there has also been several lattice calculations in the TCC sector, and what I show here is only a few recent lattice calculations which could extract some scattering parameters related to this. So there is quite some interest in studying this TCC kind of channel. Now I actually go into how we are going to explaining how we actually try to extract these scattering parameters by using lattice simulations. So this I actually start with some continuum idea. So we know that we actually identify these particles or the peaks in the cross section, identify these particles as peaks in the cross section. Right, this is also associated with a scattering phase shift. Assume that this is actually an elastic scenario, and this is possible because from the experience we know that there is a continuum spectrum of finite state that we can scan. But on the lattice, we have only finite levels. We know from our condensed matter physics courses that if you put something on if you put a Hamiltonian in the lattice, you have only a discrete spectrum. So basically, you don't have any branch cuts, you don't have any Riemann sheets, you don't have any resonances, you cannot actually pursue this kind of idea in a straightforward manner. This was actually pointed out by Mohanty and Testa in 1990. In fact, later on, Martin Luther said that it's not entirely hopeless. We still can actually associate the finite volume energy levels or finite volume information that we extract to the infinite volume physics through some simple mathematical functions. And I don't want to actually give the functions, but I just want to motivate you how we do it. In fact, actually, so this one actually I gave you an example where we just did a simulation for one particular lattice QCD ensemble. You can go on increasing more, increasing your number of ensembles that you study, or else you can also increase the kind of system that you do. Means you can actually boost your frame in finite volume, where unlike in the infinite volume, means you cannot simply boost back because you are in the finite Euclidean space. All right, so you get extra and extra levels from finite volume simulations, and you get your infinite volume physics, or you constrain your infinite volume physics better and better. So this is the way you actually extract the scattering information from finite volume simulation. Just to give you a brief idea in this slide without any figures. So if you put two particles on the lattice, we know from simple dispersion relation what will be its total energy. You can put in the momentum for this particle, you get the total energy. Now, if these particles are interacting, let's say if the particles are non-interacting, this is the energy. But if the particles are interacting, then this momenta that enters into this dispersion relation will be shifted by a delta, and this is called the scattering phase shift. And this is exactly what we are after. So what basically we are looking at is we actually do some finite volume simulation. We look at how much the finite volume spectrum that we extract deviates from the non-interacting expected spectrum, and that gives us information about the infinite volume phase shift, and this is exactly the procedure that we do. Just to give you some more idea, so this is the scattering amplitude that we deal with for this two particle system, and this can be actually written as written in a form like a real part and an imaginary part. And what we are after is looking at the poles of this scattering amplitude by looking at where this goes to zero. This is actually T inverse. So I am actually looking at poles of T. And what this Lucius prescription, whatever I discussed here, what this provides is a way of evaluating this K code delta using finite volume energy levels. Once you have once you have a list of such K code delta for different energy, you can actually parameterize your energy dependence of the scattering amplitude, and then you can actually extract the information about poles in the scattering amplitude. All right. Before I go on to showing some results, how much time? 15 minutes. Okay, I have time. So before I actually go into showing some results, let me just give you. So this is something important, otherwise you might not get the idea. So you have a two particle scattering, and in two particle scattering you have a unitarity cut in the scattering amplitude. that starts from the threshold and is conventionally taken to go towards positive infinity. And in this kind of situation, so this cut can be viewed as actually a connectivity between two. So this is coming because of the square root function that appears in this scattering amplitude. And that means square root function is actually a double valued function, which is actually leading to a Riemann structure with two sheets. And this unitarity cuts basically connects the physical sheet to the unphysical sheet. And hadrons in the real world is understood as poles in the scattering amplitude. And considering the unitarity and analyticity of the scattering amplitudes, poles are allowed to exist only in certain regions of these sheets. So resonances that we naively talk about, which can decay into some lighter products, they are expected to lie only on the second sheet, sheet 2, away from the real axis, while bound states are understood as to lie on the real axis below the threshold. While there is also some other category of poles called virtual bound states, these are also allowed by unitarity and analyticity, except that this is not discussed that well in detail. And this is an excellent example of such a virtual bound state scenario. So here actually we did some lattice calculation of D star scattering. This is relevant for the TCC that I actually have been stressing upon a little bit. And here you can see on the on my right hand side, you can see the spectrum that we extract from the finite volume, and we compare that with the non-interacting levels. So these points, the data points, are basically the simulated energy levels, while these continuous curves are non-interacting expected non-interacting energy levels in these different finite volume lattices. So you can see that there is clearly some deviations which indicates interaction between the D and D star kind of particles. And from this deviation, you can extract the P code delta, which was basically this quantity K inverse, as you can see here. So once you have such P code delta for different energies, you can just fit it and try to figure out where is the pole. Now you can see that here what I have plotted is P code delta versus P square. So this is actually the energy dependence of the P code delta. And I also plot another curve, which is basically, I call it as constraint curve, which is basically the square root of P or square root of K. All right. So whenever these two quantities crosses, there exists a pole, because this at this point T goes to 0. That means T inverse goes to 0. That means T is infinite. So that leads to a pole which is actually which we relate it to the physically observed or experimentally observed TCC. And how we do it is what I will discuss in the next slide. So this calculation was done on a 280 MeV iron mass, and we find a virtual bound state, unlike in the real world where it was found to be actually a sort of bound state. If you want to call it's not really bound state, because it was observed in the it was observed in the DD pi finite states. It was observed in the DD pi finite state. This is also a strong decay threshold, but this is actually 3 particles. So at the moment we ignore all the 3 particle effects. So if we simply ignore the 3 particle effects, we can actually consider this as a bound state in the DD star system. Okay, so what we actually try to do is that we find a virtual bound state, and how we relate it to the real bound state is or the so-called real bound state in related to this TCC is as follows. So we try to actually change this heavy quark mass and try to see how it actually varies. Unfortunately, this video doesn't work in this screen. If you are interested, you can actually look into this PRL supplemental material where this video is also given. So we basically try to argue this as some interaction between D and D star mesons in terms of some simple quantum mechanical potential, and you can try to study how the bound state position or the binding energy of such a system varies if you change the potential strength or if you change the extant particle mass, etc. Okay, and this way we know that actually if you increase the heavy quark mass, this virtual bound state will eventually become a bound state. And similarly, I said that this calculation was done at a 280 MeV iron mass, and if you try to make it towards the physical iron mass, then also it is found that it is going towards the bound state scenario. And this was actually evident from this figure where I actually showed these things. So basically what is plotted here is the inverse of scattering length, and the inverse of scattering length, the place where virtual bound state become a bound state is a place where the signature of 1 by A naught changes. And you can see that at different heavy light quark masses, so starting from m pi equal to 411 MeV, close to the very near physical iron mass, it is actually going on dropping. And in this calculation, they also tried extracting the DD star potential and tried to actually vary the pion mass information in this d discharge potential, which led them to with which actually they found that it becomes at the physical pion mass, it really becomes a bound state. All right, really becomes a bound state, very close to this real world observation. All right. Now, this is not end of the whole calculation, because this calculation has been done at 280 MeV, and all these different heavy quark mass, everything is not yet tuned. But there is something more crucial about this. Okay. Maybe I just say about this as well. So this another calculation that we did with Archana and Nilmani, and you will get to hear about this calculation from Archana's talk on Friday. And here we actually tried to study very similar system, except that we replaced one of the charm quark with a bottom quark, and we found that in this particular case, this leads to a sort of deeply bound system. All right. So what I was actually trying to take you to is an extension for the TCC calculation. So we actually found that there is a virtual bound state, and eventually it becomes a bound state. But then later people came up saying that, okay, you see, there are certain assumptions that you made in the calculation which are wrong simply. And it is not just because of our ignorance, it's because that we don't have the formalism to really attack this problem. So that's why we just limited ourselves. Now the formalism itself is actually getting developed, and in fact, actually very recent calculations, you can see that this was reported into 2401. And okay, this here actually they don't really propose anything, but here they propose some new way of attacking this problem. I will get into the problem in a second. So the problem is exactly this. So there are two things that we consider here. One is actually an effective range approximation. We basically parameterize the energy dependence of the scattering amplitude with something called an effective range approximation. And we also consider the analysis only with a two particle going to a two particle kind of system, which actually leads to some Lucher's quantization condition, which doesn't incorporate something called an LHC effect or left hand cut effects. This is actually related to a pion exchange, because it actually, both of these assumptions doesn't assume a third particle. And if there was really a third particle, which is actually indeed the case in case of TCC, because it was observed in a DD pi kind of final state. In that case, our calculation was also done in a unphysical setup where we used a m pi equal to 280 MeV, which leads to an off-shell exchange of pion mass, off-shell exchange of an off-shell pion, which actually leads to a branch cut below the threshold. And this is why it is called a left-hand cut. Okay, and this cut is actually a logarithmic cut, unlike a square root cut, which leads to more infinite set of Riemann sheets. It's actually a complicated problem. And so these people actually in this article pointed out that you have actually assumed these things, and these are critically wrong, which means that actually the final conclusion that you get a virtual bound state is not exactly correct. Although our simulation, everything, the finite volume spectrum, everything is safe, the final spectrum scattering amplitude extraction is flawed. And they argued that it's not virtual bound state, but something called virtual resonances. This is actually a bit more newer concept, and something called virtual resonances, which actually exist off the real axis in the sheet that I actually showed in the second sheet and away from the real axis, below the threshold, sorry. So this is why these are called virtual resonances. So they claim that this is the case, and they actually demonstrated in this article that this is indeed a virtual resonance. Now, there is an alternative way of getting away with this problem. So in this HAL QCD approach, the plot that I showed a compilation of pion mass dependence of this TCC. In this calculation, this pion mass dependence plot was taken from this paper. And in this calculation, what they did is they basically extracted d star potential from the lattice. And what they did is they tried to investigate the large distance behavior of this potential, which actually is crucial to determine such a shallow bound state. And they find that actually this large time behavior is consistent with a two pion exchange. So here actually this is a part of the potential that is crucial for the large time behavior, where n turns out to be 2, n equal to 2 is more important, which means that actually there is no one pion exchange that is dominant in this kind of system, which with which they argue that LHC effects due to a one pion exchange is not really important. And this way actually they tried to extrapolate it below the threshold and got a very similar, reached a very similar conclusion as virtual bound state. Now, an alternative or a more rigorous approach there are two different approaches. One is actually proposed by Dumeng et al. Here actually what they said is the main problem is that you actually start with the system where you actually partially project every kind of scattering. Instead of that, if you just don't do a partial wave projection, but collate everything, all the scattering, and do an expansion in the plane wave, and also work with an effective field theory which incorporates such a one pion exchange, then you can actually extract the entire information using this procedure. So they basically don't use a Lucius approach, but something similar, and try to get the results. And they find that actually the final results leads to a consistent finite volume spectrum as ours. An alternative procedure is to actually go for a more rigorous Lucier-based quantization condition, which also includes a 3-particle kind of scenario, where you can also include where you can also consider the third particle is going off shell. But the problem is, of course, this is actually the most rigorous procedure, and if somebody could do it, that could actually be a major breakthrough. But the main reason why it is actually a major breakthrough is because of the demands of this kind of procedure. It actually demands a lot of things from the finite volume, which includes not just 2-particle finite volume spectrum, but it also needs 3-particle finite volume spectrum, which you cannot see it actually because it is hiding this thing up until the 4-particle threshold. All right. So I now leave the TCC part and go into the other parts. I have 4 more minutes. I will just quickly glimpse through these things. So now you have already seen that it's not just the DD star scattering amplitude that are interesting. You can already see that D pi scattering amplitude is also interesting from the TCC perspective itself. But there are also other prospects in this regard. There has already been some interest in the D star scalar resonances in the D0 or the charm light sector and the charm strange sector, which were found to actually have some slightly different features. I don't go into those old calculations. You can see a list of calculations that has already been done in these non-explicitly exotic channels. While in this channel, in very similar channels, actually, there has already been observations or discoveries around 2900 MeV, which are now called as TCS, because we know that they have non-zero electric charge, which really means that actually they have some non-trivial or 4-quark content, or 2 quark and 2 anti-quark content in them. All right, so I just glimpsed through 2 of those recent calculations. This one is actually not really an explicitly exotic channel, where they actually try to extract a d pi amplitude and have some ion mass dependence. While here this is actually a summary of a similar calculation, but in the explicitly flavor exotic channel, where you can see that this is CS and 2 light quarks in it. So basically there are 4 quarks in it, which basically leads to a conclusion that they also see a virtual bound state kind of scenario. So there is definitely some attraction between D and a K meson kind of system, but it only leads to a virtual bound state kind of scenario. All right, towards the pentaquark. So there has already been some observations from experiments in the pentaquark regime in the Jepsi P finite state. There has also been observation in the Jepsi lambda finite states, for which there is no lattice investigation. But for this particular case, there is one lattice calculation which actually tried to concluded that actually at least one of the state is related to a sigma d bar kind of bound state, and the other one possibly related to a sigma C d bar star kind of bound state. While they cannot, means there are 3 particles that are observed in the experiments, while they could not really pin down whether this is related to any one of them or if this is something more complicated. All right. So now into the charmonium. This is actually a bit more complicated part. You already saw this plot. Something that I want to actually highlight is about this 3960 particle that was highlighted in one of my previous slides. There are several different other kind of experiments. So here you can see that this is from Babar, this is from Belle, this is from LSCB. All of these are possibly related to the same state. And in fact, actually there are also phenometric studies supports that there exists some kind of near threshold DS bar kind of molecular state. While there is also another feature, okay, this is something more interesting. So there is also yet unknown bound state in the DD bar kind of system, which is yet to be observed in the experiments. Okay, so there is quite some interest in the scalar charmonium as well, and this is what I just want to glimpse, because there are some results from our side, and there is one conflicting results in the recent months. So just wanted to highlight. So we actually find that there is indeed a very shallow bound state in the DD bar kind of scenario, and equivalent DS bar kind of bound state is also sort of observed. And there is another very broad resonance that is also observed, where you can see that these are the scattering amplitudes associated with these different finite state scenarios, and this is the position of the bound state that were observed. In fact, actually these calculations were done on just 2 ensembles with some not so not so very state-of-the-art lattices. These is actually 0.086, but yeah. There is a recent calculation from HADRON spectrum collaboration. In this regard, they actually did, this calculation is way more rigorous than our own. I would really admit that it's way more rigorous, but the calculation was done on a much coarser lattice and at a relatively heavier pion mass. And they find that they don't really find, I need maybe 1 or 2 minutes. Okay. So they basically exclude all other states other than the Chi-C1, other than the standard Chi-C0 that they that is established, and one more state that is closed, that is the broad resonance. All other shallow bound state they exclude from their calculation. It is not yet clear whether this is related to, also means, okay, they find that there is one state, one excited scalar harmonium for sure, but it is not very clear whether it is related to any of these features or if it is something different. And since there are quite some difference between the lattice calculation, lattice ensembles that are used, it is not yet clear if there is something that we are missing, or that something that we don't really understand between, if we compare, when we compare these two calculations. All right. Final slide on the results. So there has also been some calculation. This is not really recent, where the set C kind of set C3900 state was studied by a quite different approach called HAL QCD approach, where they try to extract the scattering potentials between different particles in a scattering channel. In fact, actually, they don't just study potentials within a scattering channel. They basically build potentials between within a coupled channel system, including 3 different channels. And they find that this kind of state that is observed in the experiment is not really a conventional state, but is actually a result of a threshold cusp. It is actually an interaction between multiple scattering channels leading to a peak kind of behavior, which we basically finally interpreted as a state. All right. So that leads to my summary slide. So I basically reported on various lattice calculations on XYZTP. By now you know what is XYZTP. And study of elastic resonances and near threshold resonances are sort of established, except that there are new challenges that are coming up even in the elastic scenarios. Once we go to inelastic setups, more and more higher and higher lying exotic hadrons, things become much more complex because we have multiple scattering channels, more parameters to constrain, more means we have to constrain the energy dependence much more in a better way. I did not cover anything about baryon because I was sure that I will be in short of time, but if you are interested, you can listen, read through some of these newer articles that we have put out. Thanks.
Yeah, thank you very much for this nice talk. We have time for some questions. So what's the bottom line in terms of your interpretation of these states based on the lattice? Do you,
I don't want to actually make a claim because I have agreed to actually video record it.
Sorry?
Because I have agreed to video record it, because once I make a claim, then it can actually go viral sometimes. But I can actually say something here about the TCC. Okay. So there is a recent work that we are actually about to put out, where actually we try to study the quark mass dependence of this system. So here I already say about this thing. So basically we try to study the quark mass dependence, and quark mass dependence means we can actually relate it to the reduced mass of the system or the exchange particle mass, etc. And based on that, we know that actually it is like, so if this has to behave like this should be a molecular bound state. So this is most possibly, so TCC is most possibly a D star kind of system, but I don't want to exclude a compacted Tucker feature at the moment, because we are also working on that part. We have some interesting results on that side as well, although we haven't made any interpretations.
But you're saying that both can describe your data?
You see, I don't want to. So thing is, this is actually a wrong concept to associate one picture to a particle. This is what I feel. So a particle or a feature that you observe in the experiment can be a result of different pictures. It can have different strengths of four components into it. So for example, if you,
so it's like a linear combination.
So it could be a linear combination of different things. So there could be, it could be the thing that, so typically shallow bound states are more related to molecular bound states. This is what I feel. But it could also happen that there is a real pole, which is actually not a result of molecular interaction, but actually a compact interaction, which happened to be, coincidentally happened to be close to the threshold. So that actually spoils the interpretation. So it could be that the state that we observe could be dominant with certain picture, but it could also have some subdominant fork components from Tetacore kind of thing.
While people are thinking of questions, I mean, so you said at the start of your talk that you know, there's this word exotic, which means things that are not sort of understood. And so is there, based on this analysis, what is still exotic?
We have actually excluded all the particles here because each particle takes quite some time. So at the moment, at least if we just talk about my own research, I have been focusing only on 3 or 4 particles till now. I feel that actually TCC is becoming less and less exotic, while X3872 still remains to be an exotic. I have done a calculation on X3872. I did not actually show it because I feel this is already outdated and I don't want to. So this is already like 8 to 9 years old. And if we were to do such a calculation now, we would do it in a much better setup. I do not want to show it. But the thing is, X3872 still remains to be an exotic, while TCC is more and more becoming less and less exotic. Yeah.
Okay, so there are no more questions. Let's thank the speaker for a great talk.